Professor Curtis, your instructor for this course, and this is the lecture video for Chapter 31, Light Quanta. Let's get started. To begin, we're going to do a little review of history. It will put into perspective some of the, controversies that scientists were encountering in the late 19th century. So we go back to classical times when the ancient Greeks were living, and their description of the physical world, what we call classical physics, deals with two categories of phenomena. So we've got particles, which are tiny objects that have mass. They travel through space in straight lines unless some force acts upon them to move them in a different direction. And then we've got waves, phenomena that are extended to space. They can diffract, they can interfere. So waves and particles, two different types of phenomena. What about light? Is light a particle or is light a wave? This is the question that's been asked all throughout the ages. So starting back with the ancient Greeks, we've already heard about Euclid. Plato was a famous Greek philosopher, student of Aristotle, who was a student of Socrates. And they would say that light consists of streamers emitted by the eye. Interesting how they thought that light came out of the eye, whereas today we know that light actually comes into the eye, but that's what they thought back in ancient Greece. The Pythagoreans, also ancient Greek mathematicians, they claim that light emanates from luminous bodies as very fine particles. And then some dude named Empedocles, I guess I'm getting that right. He looks like, the picture makes him look like a Greek Arab. I don't really know where he's from, but anywho, he said that light is composed of some sort of high-speed wave. So already we've got the particle wave controversy going back to ancient times. Then, of course, Sir Isaac Newton comes along and claims that light is a stream of particles. This is really amazing he would say that, because in his grand treatise on optics, he describes many experiments that he had with prisms in which light clearly displays a wave type phenomena. So, it's amazing that after all these experiments that show that light has wave properties, he would come out and say that light actually is a stream of particles. A scientific colleague that came a little later in time, Thomas Young, clearly on the side of waves, saying that light is a wave from his famous double-slit experiment. If light does not act as a wave, there's no way you can explain the results of his double-slit experiment. And for many years thereafter, many scientists sided with Thomas Young. So you've got James Clerk Maxwell, who says that light has to be a wave. That seemed pretty clear from Maxwell's equations that he developed. And then another scientist of the day, Heinrich Hertz, said that light is also a wave. Heinrich Hertz is the guy who proved that EM waves actually exist. It's not just theory. So Maxwell's not just, coughing up some mathematical philandry that he came up with over the weekend while he was sitting in his armchair. No, EM waves actually do exist. So after Thomas Young, we get the science basically leaning towards the idea that light is a wave. Which brings us to the birth of quantum physics and a German physicist named Max Planck. Now, Max Planck, commissioned in the late 1800s by electric companies, they were interested in how do we get the most bang for our buck. So how do we create maximum light from light bulbs while supplying them with a minimum amount of energy? So here's Planck in 1878, tasked with solving this problem. And he threw himself at it, and in the process of trying to figure it out, he came up with another question, which is, why is electromagnetic energy emitted only at specific frequencies or energies? In trying to get maximum light from the light bulbs using minimum energy, he noticed that the light was emitted from the light bulbs only at specific frequencies or energy levels. So why is it that you can only get specific frequencies and not something in between? Why can't you get anything you want? Why are there only a certain set of values that you can get and nothing else. Well, in attempting to solve that problem, because again, he's getting paid by the electric company and they're not going to fund his research forever, eventually they're going to want answers. So he ended up making a hypothesis that he called, quote, an act of despair, because in his desperation to get an answer before these, rich guys who own the electric company were going to lay in on him, he used theories from Ludwig Boltzmann, of which he was deeply suspicious. Now, Boltzmann, famous physicist, mathematician, he certainly made some contributions that were noteworthy, because there's a constant of nature named after the guy called the Boltzmann constant. So when they name a constant after you that describes a number you see over and over again in calculations, you're not a lightweight, you're a heavyweight. So Boltzmann, he could hold his own, but Planck looked at some of Boltzmann's ideas and said, you know what? This guy's smoking crack rock. I don't really think that he knows what he's talking about. But the only way that he could actually come up with a solution that made sense to his problem was to use some of Boltzmann's theories. And so, in an act of despair, as Planck calls it, he used Boltzmann's theories to solve his problem. He ended up stating that radiant energy is emitted in discrete bundles, which are called quantums. And this hypothesis became the basis of quantum physics. Yeah, that Boltzmann's a real putz, and I'm an even bigger one for agreeing him. You could be sure that's exactly what Planck was saying back in 1878. So here's Planck in 1878, and he went on to do more experiments in physics. So by the time we get to 1901, this is what he looked like. So the moral of the story is, don't even try physics. I mean, there comes a point where you just go too far and you just don't want to go any farther. So please do not pass that point of no return. Here's Planck in 1933. You can see he's not a very happy man. Of course, in 1933, the Nazis are ruling Germany, so there's lots to be unhappy about. But in his hypotheses, with light quanta, he went on to describe photons as corpuscles of light. And he also described the amount of energy that a photon has. And this is where we get Planck's constant. So the relationship is E equals hf, where E is the energy of the photon, h is Planck's constant, it's a constant value, and f is the frequency of the photon. What this says is that energy of light, and in fact all EM waves, because light is just a separate example of an electromagnetic wave. It's a specific type of electromagnetic wave. Basically, the energy is a whole number multiple of individual quantum. So they're discrete values. You can't get something in between. And the smallest amount is just one individual quantum. So you can have one quantum, or two quantums, or three quantums, or four quantums, but you can't have 1.5. You can't have 2 4/4. Well, actually, you can't have 2 4/4. That's 3. You can't have 2 3/4. And so light exists on these levels of quanta. The energy in the light corresponds to a discrete amount, a whole number multiple of an individual quantum. Planck kept holding on to his wave theory nonetheless. I mean, really, this whole idea of quanta really suggests that light is a particle and not a wave. And so he held on to the wave theory, holding that, something's going to prove his earlier theories and hypotheses wrong, but it was not to be. Planck was actually on the right path. So exactly how big is Planck's constant? Well, it's actually a very, very, very small number. So 6.626 times 10 to the minus 34th joules per second. So what that means is the times of 10 to the minus 34 means you take that decimal point and move it over 34 places to the left. So if you're not adept at scientific notation, you can write that out by moving that decimal point 34 places to the left, and you'll basically get this number right here, which you can see is a very, very small amount. But it keeps coming back up over and over again. When you look at these calculations in quantum physics, this number keeps popping up over and over again. So h, as Planck's constant, is a fundamental constant of nature, because it keeps showing up over and over again. Like pi keeps showing up in geometric areas and volumes, and then c, the speed of light, is a constant. It keeps showing up again and again. So Planck's constant is in that neighborhood. This equation says that light is not emitted continuously, but as streams of photons. So in other words, you get a whole number, multiple of one quanta, which is represented in Planck's constant. So each stream of photons, each of the photons in the stream has a frequency of f and an energy of hf. This relationship also tells us why microwave energy doesn't do the same damage to living cells that UV light does or X-rays can do. Microwaves are low frequency. Low frequency means low energy. And UV photons are high frequency, high energy. And in fact, they're so high they can deliver 1 million times more energy than a microwave. So, what type of EM wave your photons are coming from makes a big difference. So now we get to our first activity for the lecture. So in your workbook, I'd like you to use Planck's constant to find the energy level for different colors of light. So here we've got red light, which you can see the wavelength there, 650 nanometers. Green light with a wavelength of 510 nanometers. And violet light with a wavelength of 400 nanometers. So go ahead, stop the video here, run your calculations, and then when you get done, come back and we'll see how well you did. Okay, let's see how well you did with this. So the red light is going to have a frequency of 4.62 times 10 to the 14 hertz. We get that by taking the speed of the wave, which is the speed of light, dividing it by the wavelength, which you can see the 0.00000065 meters. That gives us the 4.62 times 10 to the 14th hertz. We then multiply that frequency by Planck's constant to get the energy level, and we come out with 2.89 times 10 to the negative 19th. Green light calculation runs the same way. We have a frequency of 5.88 times 10 to the 14th hertz, and an energy level is 3.68 times 10 to the minus 19 joules. And finally, the violet light has a frequency of 7.5 times 10 to the 14th hertz, and an energy level of 4.7 times 10 to the minus 19 joules. So using those two equations, the first for wave speed and the second for energy level, we can find out a relationship between the wavelength and the energy level. So for the red light, which has the longest wavelength, we find we have the smallest energy. For violet light, which has the shortest wavelength, we find we have greater frequency and hence greater energy. This brings us to the photoelectric effect, which was an experiment run in the late 19th century by many scientists because they were trying to figure out the nature of light. So after Young's experiment, it's pretty much decided, there was a consensus that says, yes, light is behaving like a wave. But if light is a wave, then some of the results from this photoelectric effect experiment don't really make sense. The photoelectric effect is where you shine a light on an electrically conductive piece of material. So you've got, say, like a metal plate there that's been bent inside the glass tube. You take all the air out of the glass tube, so now the metal plate's in a vacuum, and we'll shine light into the tube. the light waves encounter the surface of the metal, and the surface atoms of the metal are agitated. They become excited because of the extra energy from the light waves that are coming in. So that excitation actually creates a current to jump through the ends of the circuit there that you see inside the glass tube. And so there's an actual flow through the circuit, and this is what we call the photoelectric effect. Many researchers, as I said, were investigating this effect, and they were trying to make sense of some puzzling results. The first was, if light is really a wave, then electrons should need more time to build up the energy to eject under dim light, but they don't. You shine the dim light on the metal plate, and boom, the electrons just fly off. Wave theory predicts that brighter light will increase the maximum energy of the electrons, which makes sense. Okay, wave theory, brighter light, higher amplitude, it's going to have more energy, and therefore you would expect it to eject it off, but it doesn't. However, violet light produces the effect more easily than red light, so there is some difference there from the wave nature of light, but some of these effects would make more sense if light were particles and not waves. But how can light be both a wave and a particle? That's what was puzzling scientists. Also, if you increase the brightness of the light, you increase the number of electrons, but not their maximum speed. So again, more evidence that light is actually a particle, but light can't be a particle, because then what do we say about Young's double slit experiment? It's clearly a wave. You see, there's a conundrum here where we've got evidence that it's one, it's got evidence that it's another. So how do we make sense out of all of this? This is where Einstein came onto the scene. In 1905, called his miracle year because he published a number of different papers during this year. And in one of those papers, he resolved this apparent contradiction. He actually proved that Planck's act of despair was correct. And then he took the next step beyond that. He said light interacts with matter not in continuous waves, as Maxwell said, but in tiny packets of energy, just like Planck said. The number of photons in light produces the brightness of the whole beam, but the frequency of the light determines the energy of each individual photon. So you've got two variables here that are related and yet not quite related. There's not a real direct connection between the two of them. Of course, these ideas were almost universally rejected, even by Planck. Remember, Planck was holding out hope that his earlier hypothesis would be disproven. But Einstein turned out to be right, and he suggested that light actually has properties of both waves and particles. This is why we see results in the experiments from both sides of the fence. So the fact that there's interference with the light waves proves that it has wave properties. However, the photoelectric effect proves that light has particle properties. So which are which? And this is what Einstein proposed. He said photons behave as particles when they're being emitted or absorbed. They behave as waves when they're traveling from a source to where it's detected. So when the light interacts with matter, it behaves as a particle. But on the way there, it behaves as a wave. So this explains some of the effects that we see. So if you take, say, light and you put it through, so you've got weak light, they're putting it through a slit. You get 28 photons to go through, and you get an image there, and it looks like wave. It actually looks like you've got a particle effect there from the light. But if you increase the number of photons there on your image to 1,000 and then to 10,000, well, now you can start to see those fringe patterns start to develop, which suggests that light is behaving as a photon when it strikes the photographic plate to create the image. So when it interacts with matter, it behaves as a particle. But the fringe patterns come from the wave properties of light. So on the way there, it's exhibiting properties of a wave. French physicist Louis de Broglie actually took Einstein's ideas to the next level. He proposed that every particle of matter is somehow endowed with a wave to guide it as it travels. So it's not just light, but it's all matter. So the relationship to determine the wavelength of that wave form its guiding matter as it travels is h over p, where h is Planck's constant and p is the momentum. So the wavelengths are called de Broglie wavelengths, after de Broglie, who proposed the theory. And of course, h is Planck's constant, m is momentum. So what this says is that under proper conditions, every particle will produce an interference or diffraction pattern. Well, obviously de Broglie wavelengths are significant only if the body in question is small, okay? Because remember, Planck's constant is a really small number. So when you take a really small number and you divide another number into it, you get an even smaller number. So the only way that de Broglie wavelengths are going to be significant in any sort of calculation is if you're looking at a body that's really, really small, like an electron or some other atomic particle. Well, this raises the question of how do we measure the properties of very small objects? A wave, by its nature, is going to occupy some space and last for some time, but it can't be squeezed into a single point in space or limited to a single instant in time. So how do we make measurements? And besides, the act of observing very small things affects a particle's position or its motion, producing considerable uncertainty. And this leads us to Heisenberg's uncertainty principle. Werner Heisenberg, German physicist. So a lot of these physics guys are coming from Germany, or the early part of the 1900s. So, this guy, you can see when he lived and died. So yeah, he lived through Nazi Germany as well. He's most famous for his uncertainty principle, which expressed mathematically, you see here, change in momentum times the change in position has to be greater than or equal to Planck's constant divided by 4 pi. Mathematically, what this inequality says is that you cannot measure both position and momentum of the same particle at the same time. Now, that may sound strange to some of you, but think about it like this. Suppose we have a billiard ball sitting on a table. So now we can clearly see the position of the ball. But remember that momentum is mass times velocity. And velocity is a vector, which means it has direction as well as magnitude. So we can determine the position of the ball pretty precisely, but we have no idea from what we observe here in which direction the ball is going to travel. So maybe it'll go this way, or maybe it'll go over here, or maybe it'll go back this way, or maybe it'll go down here. It can go in any direction. We don't really know which direction it's going to go in. So we can measure position, but then we can't get a momentum because we don't know what direction to put our velocity vector in. Likewise, if we observe this motion in the billiard ball, okay, so now we've got an idea of the direction it's traveling in. It's going back and forth. But where exactly is the ball at any point in time? Is it here? Or maybe it's here? Or maybe it's somewhere in the middle? We don't really know. So when we know the direction, we don't know the position. When we know the position, we don't know the direction that it's going to travel in. There's an uncertainty when you go to study these really small particles. Now we extend this idea of uncertainty even further if we remember that change in momentum is equal to the impulse of the particle. And impulse is just the force times the time. So that means that the change in momentum is equal to the force times the time. Well, if we substitute force and time for momentum in our earlier inequality, we've got F delta T delta X, but F delta x, force moving through a distance, is the definition of work, which is a form of energy. So we can rewrite our inequality in these terms. The change in energy times the change in time has to be greater than or equal to h over 4 pi. What this means is that Heisenberg's uncertainty principle says it's not possible to measure both the energy of a particle and the time of a particle that it takes in motion at the same time. So we've got direction and position. We can't measure both of those at the same time. And we've got energy and time, which we can't measure both at the same time. This leads us to the complementarity principle, which was proposed by Niels Bohr. Niels Bohr, the guy that came up with the atomic model of the atom, where all the electrons have a planetary orbit around the central nucleus. Quantum physics can seem confusing, but rest assured, there is a method behind the madness. There's order amidst the chaos. And Niels Bohr is one of the guys that helped to identify that order there amidst the chaos. So he was from Denmark, and he described this aspect of quantum physics in his complementarity principle. Quantum phenomena exhibit complementary properties. Okay, for example, light has both particle nature and a wave nature. Particles and waves aren't the same thing, but they're opposites, but they complement each other. They're different aspects of the same thing that serve to complement one another. And what we observe depends on the experiment we conduct. This is especially true when you start talking about subatomic particles. Since we cannot fully understand the whole without understanding its parts, even though those parts may oppose each other. So we have to understand the parts in order to get the whole. But our understanding of the parts depends on the experiment that we conduct, because what experiment we conduct is going to affect the observations that we make. So this gives us Niels' complementarity principle, and he believed in it so much that when creating a family crest for his family, you can see he's got the Chinese yin-yang symbol there in the middle, the perfect symbol for complementary. So you've got opposites that are attached to each other, they complement each other. They're opposed to each other, the yin and the yang, but at the same time, they complement each other, and the whole is greater than the sum of the parts. If you think about it, complementarity is all around us, okay? So go ahead and take a moment as we're finishing up this lecture to list in your workbook examples of items or concepts that we cannot fully understand without understanding its opposite. To give you some examples of what this is about, think about joy and pain. You really can't understand what joy is unless you know what pain is. Joy is meaningless without pain, and vice versa. Pain doesn't have any meaning unless you can flip that around and experience joy. Another example would be rest and motion. These are opposites. So a body at rest is not in motion, a body in motion is not in rest, but yet they complement each other so that they describe the totality of bodies that we can study in classical mechanics, because bodies are either at rest or in motion. So think for a moment about what are some examples of items or concepts that you cannot fully understand without also understanding its opposites, complementary pairs. And I want you to go ahead and take what you think is the most original example that you can come up with, and go ahead and just email that to me, and I'll look through the submissions, and the students who submits the most original example will get 2 free extra points on the next test. Now the example has to be submitted by email, and you must email it to me no later than the deadline for the homework assignment for this chapter. So if you're interested in getting a couple of extra free points, go ahead and take your shot, submit that in, give me what you think is the most original example of a complementary pair. And that brings us to the end of this lecture. Hope you found it helpful. Thanks for watching, and we will see you in the next video.